Hello, this is part 2 in a series of videos about CHUMP, a cheap, homemade, understandable minimal processor. The purpose of this section is to show visual confirmation that the CHUMP Beneath code written in the previous section has been successfully flashed onto the AT28C16 EEPROM through the use of LEDs. The main component of this section is the EEPROM. EEPROM stands for Electrically Erasable Programmable Read-Only Memory. This falls under the category of non-volatile memory devices, which means it can retain information even if power is turned off. Since it's electrically erasable, information can be modified or erased electronically, versus older versions where UV light was needed to erase information. This makes EEPROMs very popular in modern devices. The EEPROM used for this project is the AT28C16. This chip can store around 16,000 bits of data, which translates to 2048 bytes, hence the 2000 by 8. These bytes are organized into pages, with there being 128 pages each containing 16 bytes. There are 24 pins on this chip. There's the ground pin and the voltage pin, and it can take 5 volts. These are the address pins, going from A0 to A10 for a total of 11 address pins. These pins are used to set the memory address you want to access. Since there are 16 lines of code for this project, we only need 4 address pins, so these are connected to the program counter, which counts up to binary 15. The rest are grounded. These are the I/O pins, going from I/O0 to I/O7 for a total of 8 I/O pins. These are input-output pins and can be used to read and write data to the EEPROM. To do either, you have to configure these 3 pins, the write enable, the output enable, and the chip enable correctly. The chip enable, or CE pin, is used to enable or disable the entire chip for read or write operations. Since we want to read and write to the EEPROM, the CE pin is set active, which means wiring it to ground. If the pin is set high, the chip will ignore read and write commands, and in the future it might be useful to prevent any unintentional operations. To read the data, the write enable pin has to be set high, its inactive state, and the output enable pin has to be set low, its active state. After doing so, it'll show the data on the I/O pins from the address the chip reads from the address pins. To write the data, the output enable has to be set high, and the write enable pin is set high at first. After doing so, you can write the data onto the I/O pins, and then pulse the write enable pin, or set it low, in order to write it into the EEPROM. This is kind of hard to do on the actual CHUMP, so I built an EEPROM burner to do so. It's connected to a Nano, which runs this code to burn the data onto the EEPROM, and there are LEDs connected to show visual confirmation there. After which, the EEPROM can be put into CHUMP where it will read the data it's stored. As you can see on the serial monitor, the EEPROM is reading the codes correctly, so we're good to go. Just to show that this works with CHUMP, I'll go through my code step by step. As you can see, the yellow LEDs, which are connected to the program EEPROM, reflect my code, and the red LEDs reflect the line address. The green LEDs are connected to the control EEPROM, and they reflect the control codes. The control EEPROM is there as a replacement for the complex combinational logic circuitry that would provide dynamic control for the processor's various modules and provide storage for the machine language version of the program. I'll explain this more in my next video with the ALU. Thank you for watching.